Today I'm going to talk about some of the work I've been doing in Smokeview to improve the performance of Smokeview for large cases. Just as in FDS, there's certain inefficiencies that Kevin and Randy and others have improved for large cases. There are a number of things in Smokeview that are inefficient that don't really show up until you get to large cases. So this is an example of a large case I've been looking at. So basically today I'm going to talk about more of the mathematics and the computer science of improving the smoke algorithms. Talk about some features that are related that you may not use often in Smokeview. So this particular case was we're modeling of a fire in near Gatlinburg, Tennessee. It was you may have heard on the news a year or two ago. Now, this case was set up. It has 400 meshes. Each mesh is 100 by 100 by 60. So, and there's like 800 or more time frames. So there's a lot of grid cells, 240 million grid cells, 192 gigabytes of smoke data. So it's a non-trivial problem. Some of the challenges are the amount of memory it takes. So I don't think any of us have any computers that have 192 gigabytes. Just the bulk of the computation that's required to do that. So, and then the amount of time to load the data. So now, in a typical scientific computer program like FDS, a rough rule of thumb, if you want to measure the amount of work that it takes to do something, it's a rough rule of thumb that it's the number of multiplies that you're doing. So if you want to speed up a calculation, you want to figure out, well, how can I reduce those number of multiplies? It could be you do it in the algorithm itself, or maybe you say, do I really need all those grid cells? In Smokeview, the typical rule of thumb would be the number of triangles that are drawn. So if I can figure out a way to reduce the number of triangles but still get the same visual display, well, then that's what I want to do. So some strategies for speeding things up would be to compress the data, make use of the GPU. Sometimes you can load the data in the background while you're displaying it, and it's sort of obvious in hindsight, but if, the case of smoke, if there's no smoke in a mesh, well, don't draw it. Well, I mean, in FDS, we output all the data for all the meshes, but a number of meshes, the smoke is transparent. There is no smoke, so don't draw it. The basic equations that I'm solving to visualize the smoke is called the radiative transport equation. So concentrate on the upper half of the slide. I just have the lower half for reference. So if you can think of light coming from the left to the right, there's basically four types of interactions that we can model. One is, you have light, or just think of photons coming across. It hits a particle of soot, and so you can, that light quantity can be absorbed by the soot. It can also, scatter or bounce off the soot. Then if the region is hot, it can emit its own photons, and that would be where the fire is. And then you could have photons that are coming elsewhere from the simulation, and they could, called in scattering. They could bounce off the, that region of space into your line of sight. Now the unit of measure that that we're modeling is something called radiance. Now the way to think of radiance is just imagine you're on the surface of Mars and it's a bright sunny day, and then compare that to how you would feel on the surface of Earth, forgetting that you wouldn't be able to breathe. Now, on Mars, it's the same sun, you would feel cooler because the heat flux striking you on Mars would go down by the square of the, basically the surface area has increased. However, when you look at the sun would have the same appearance. It would appear just as bright. Now the disk would be smaller so the light would be coming at you through a smaller disk, but the brightness would be the same. So in Smokeview, we can use that to my advantage, that I don't have to worry about the distance of the light. The light is going to be just as bright no matter how far it is away from me. The only thing I have to worry about is what there is between me and the light source. So I have to account for the absorption. Now, if you take these first two terms, the absorption and the outscattering, and you combine them together, and you work out all the math, that's what you get Beer's law, which I'm sure most of you have heard of. And for the most part, that's what we use in Smokeview to model. Now, here's a sort of a rough diagram of what Smokeview does. The blue dots represent the data that FDS would compute. Now, the original algorithm that Smokeview used would be to use that data directly. So I would draw planes, connecting these blue dots and compute the opacity and the color at each one of those dots. And that's what these planes here. You never see this in Smokeview because I'm always drawing the planes orthogonal to the line of sight, but here I'm cheating and I'm rotating to the side. So this is what Smokeview is drawing. So it's a series of partially transparent planes. Now, in the original algorithm, I'm tied to the FDS grid. So earlier I said that if I want to make things go faster for large cases, I want to reduce the number of triangles I draw. It's much harder to do that when I'm tied to the FDS grid. I can only go, I can skip like multiples of 1 or 2, and but it's a lot harder. So the strategy that I'm using is to use my own planes of data. So so the black dot represents where the observer is in Smokeview, and the black line represents the direction you're looking in. So now I generate a bunch of lines or planes that are perpendicular to my line of sight that don't correspond directly to the FDS grid. So in order to make that work, I have to interpolate. So I have to compute data along these black lines, and I have to interpolate using the FDS data. In order for that to work, the first test would be, can I do that efficiently? So that was the kind of like what I was doing in the prototype stage. Now, sort of as an aside, Smokeview has been doing 3D interpolation of arbitrary slice file data before, and I just want to tell you a little bit about that. That if you set up a slice file with a 3D slice file, and you can draw planes, arbitrarily oriented planes. Now the red dot and the line represents a normal vector to that plane and the direction. So you would control the direction. You can either do it with the mouse by just moving the plane somewhat the same way you move the scene. Or you can do it with the dialog box by specifying the location of this dot and then the azimuth and elevation angle. So this just kind of shows you. Now an application would be for that with Marcos's geometry, like for this slope beam ceiling case, you could set up a slice file that would be parallel to the slope ceiling, a certain distance below. This kind of gives an overview of the algorithm. So basically, you're at a certain position, you place a number of this. I'm just showing one plane here, but you would place any number of planes depending upon the spacing that you specify. The default spacing would be the spacing of your FDS grid. Now, I'm using the same algorithm that I use to generate isosurfaces to basically find these locations of, to specify the plane. And so then you just, go back to your linear algebra and just find vectors that are perpendicular that lie in this plane, and then you just form these triangles. Now, my original algorithm was to use, I had a recursive algorithm for forming these triangles, and it turned out that it was not, writing the code was efficient. It was literally just one page of code to write the algorithm, but the problem was that the triangles were not uniformly sized. So it gets back to, I want to minimize the number of triangles. Now, and so for each of these triangles, we need to assign, a color based upon either the temperature of the heat release rate and an opacity based upon this soot density. And this just kind of illustrates, the steps. So here I'm drawing figuring out where the planes are. The next step will be to, figure out the triangulation. And then I'm going to change the coarseness. So here I'm less coarse. And then I'm going to go to the very fine mesh. And then finally, I'll show the smoke. Now, the challenge is that I have to do all this in a 1/30th of a second. I mean, in order for this to work, and that's what I didn't know when I was doing this. Are the computers fast enough now that you can do all this extra work? Now, the whole point of it is that now that I can do this, I can say instead of having a step size that's the size of the grid, I'll make it 10 times the size of the grid, just because I've run the Gatlinburg case and I want to just do a quick and dirty visualization of the smoke. Now, and this just shows, I think Randy may have shown this case. And this just shows where here you're setting the grid size within the plane, and the perpendicular is the step size between planes. Now, here is the same animation from the first slide, but I'm just illustrating the point of, well, if you don't have any smoke there, don't draw it. Smokeview originally wasn't doing that. Well, you know, for regular cases, you would never notice that the drawing, you know, smoke with zero transparency, you would never notice that it was slowing things down. But for this case, you do. Now, another strategy which FDS is doing is, the soot densities are, 4 bytes, or actually 8 bytes, but I'm taking the 4 byte single precision quantity, and I want to compress that to make it, because the ultimate opacity values that Smokeview's using is 1 byte. So there's no point really, to transferring over, 4 bytes. And so here, this is just using a simple scheme, run length encoding. So basically you take repeats, so there's 4 zeros here, so you replace that with a 4 zeros. So the advantage of that is when you decompress it, it's very, very fast. Now, another method for visualizing smoke is, the first method we're using blending. So basically, you take a linear combination of the colors that you're drawing with the colors that are currently in the buffer. Now, what this is doing is saying, if you've got a very bright fire at some region, use it no matter if it's brighter than what was there before, and don't take into account anything that's there before. So, basically, so here's an example. You've got a gray here that's, with the RGB values of 192 each, and the current screen buffer is 128 each, so it's a darker gray. So the max algorithm would use the 192, whereas in this case, you would use, you wouldn't replace the 64s. Another method for speeding up is to use SmokeZip, and that's what I'm using for these 3D slice files. So here's the same fire using this max method. Now, one of the things I want to do is figure out how can I have my cake and eat it too. I mean, here I'm not really solving the radiative transport equations directly. I'm using this strategy for drawing the flame. When we were using the blending method, what would happen is that the stuff that wasn't bright was dominating the scene, and I think that was happening because I don't have enough digits in how I was doing the computation. So anyway, that's sort of an area of work. I want to fold this into the more physics-based approach. Now I want to spend a few minutes on making movies. Basically, I don't want to reinvent the wheel, so there's a couple of, there's a public domain program called FFmpeg that is pretty good, and it's available on the PC, Mac, and Linux platforms. Now, if you can just, you don't need to remember the link. If you just Google search FFmpeg, you can find it. Basically, if Smokeview will add a couple of dialog boxes to use these programs if it finds FFmpeg in your path. And so I want to talk about making something called a 360 video, and that's basically an animation where you can change your, it's one animation, but you can change your point of view and look in all directions. So basically, when you're making a movie, if the blue dot represents where you are, and if the rectangle represents the screen that you're on your computer, what Smokeview is doing is it's just projecting your 3D scene onto the screen. Now with the 360 video, what I'm doing is I'm looking in all directions. Here I'm just showing 8 different views, and so if this rectangle represents the final image that I'm generating, each image, think of it as the Mercator projection of the Earth. So if longitude goes from left to right and latitude, so this is the North Pole up here, so I'm going from minus 90 degrees up to plus 90 degrees, and here I'm going from minus 180 to plus 180. So every pixel in this rectangle, you can think of having an azimuthal and an elevation angle. So what Smokeview is doing is it's figuring out, okay, so for this pixel right here that I'm pointing at, which one of these 26, or in this, 8 squares is that pixel located? And so then I just copy it over. Here just showing the same thing with all 26 views, and then a picture of the Earth. And here's a test case with, just the blue dot is in the exact center of the scene, and then I've colored the 6 sides of the box with 6 different colors, and this just shows, how the colors get mapped. Now I'll show you the just show you a little bit. So you can see it looks weirdly distorted. So this is just a regular view showing the literal image. So you said Alt-Tab. So now, this animation is playing, so now you can move it around. Now, a couple of interesting things. Now, if you do a Google search, I know most of you have smartphones. If you do a Google search on 360 player and either Android or iPhone, depending upon which kind of phone you have, you can install these apps, and then you can play these animations on your phone. And what's really interesting about the phone is it's better than the PC because the phone knows which direction you're looking at. So when you turn around and look up, the video changes to match. And I'm sure you can go to YouTube and find, examples of what a lot of other people have done. And I'll show you some of my warts. This is one thing I'm working on. Let's see. This stair stepping shouldn't be here, so I have to figure out where the error is. Unfortunately, I figured out it's my fault, not OpenGL's fault. So, well, that's pretty much what I have. So I've got 30 seconds to spare. So thank you.
Thanks, Glenn. Cool stuff to see. Questions, comments? Donna says, wow. Anybody else? And this stuff is all experimental right now, right? Is that correct?
Well, it's experimental, but it's in there. I mean,
It's in the nightly Smokeview builds, so.
Yeah.
Okay.
So, I mean, and I would say, I can't, it's hard in a 20-minute talk to explain everything, so feel free to send me emails or use the user forum or so forth and also I've been working on a wiki on making movies that has some of this stuff in there, so, so if you have questions, I'll, feel free to contact me.
Sounds good. Randy.
I know Smokeview has some capabilities for lighting. Is there, I mean, how far away would lighting the smoke be? Is that non-trivial or what?
Lighting is in there. I have to go back and see what state it's at. I mean, I was never really satisfied with it, so I didn't really make it part of the official, but there's something, I'm doing something called single scattering, and basically, if we go back to that slide, let's see. The in-scattering is what's hard, and because basically to do it right, you have to integrate around around your location, and there's something called single scattering, which means basically you only consider one interaction, and because smoke that most of the smoke we deal with has low albedo, which means that the probability that a photon is absorbed by the smoke is very high. If there's a 90% chance that the smoke gets absorbed in one interaction, there's, it's, in two interactions, it's almost certain. So you can, I'm sorry, go ahead.
It's hard is kind of what he's saying. So,
yeah.
And hard to get right.
So it's in there. It's one of these things I have to go back and dust off and take a look at again.
Yeah, and I was mentioning the other day too, it depends on condition. Like a fire in this room, lighting the smoke might not make as much difference because it's often not going to have that much ambient compared to everything else. But for your outdoor case, you know, when you look at a picture of a wildfire, there's a lot of light from the sky that does color the smoke. So it's kind of
like
realistic.
If I were to show you a picture, forget smoke. If I were just to show you a picture of, some a case with blockages, Smokeview actually lights the blockages. So if I were to turn the lighting off, it would be flat and it would be much harder to see the three-dimensionality. So, so having lighting in the smoke would add more structure.
Right.
And
you had another comment, Randy?
Yeah, well, my question is actually for the Thunderhead guys. So are you guys doing single direction, what do you call it, in scattering for those videos you showed?
I'm actually not certain what algorithm our graphics guy was using for those test videos of smoke. That was just like a first try. So, I mean, we're kind of in the same location. We haven't really thought through it and figured out we don't want to make it just look cool like the movie guys do without it being at least, close to right. But that's something that we're working on as well. Any other questions, comments? All right. Thanks so much, Glenn.